8.3 part 2, we're going to look at areas with polar curves. So let's take a look at what we have here. So think back to when we have earlier sections and classes. We had a sector of a circle. A sector of a circle is the region bounded by two radii and a central angle, and the arc intercepted by that angle. The area of this sector is 1/2 r squared times theta. Theta is measured in radians. How can I use this to help me find polar areas? Okay, so let's take a look. Consider this graph right here between 0 and 2 pi. Find the area of the shaded region. Well, in rectangular coordinates, we would take the limiting sum of rectangles, Riemann sum, find the area under the curve. In polar, we're going to have the area will be something to do with this area of a sector up here. So here's how it works. Instead of doing rectangles, we're going to do little sectors. We're going to take this graph, and I took a little piece of it here, and we cut it up into little sectors, okay, based off of from the pole area outward. Okay, and then for this region right here, which I then blew up even more, I'm going to take and approximate it using an area of a sector. So I have some point on this curve, and from here I'm going to make this the arc right here. So then I have a radii here and here, okay, and an angle right here. So this is a sector piece. And the area of that sector is 1/2 pi r squared theta. And you can see that it's not exactly the same amount. It's an approximation. And using the same concept that if I take this to extremes, in other words, if I make this angle smaller and smaller and smaller, I'm going to partition this region into thinner and thinner little sectors. Okay? And this will allow me then to take the limit as n goes to infinity, which is what we did for rectangles. And we end up with this right here, where I'm taking the sum of all of these little sectors and adding them up. We have two angles here, the start angle and then the end angle. And so this is how we get our formula right here for the area under the curve of polar. Okay, and so this is what you want to remember right here. And so here we go. Let's go do some problems. Okay. So, starting with this one right here, write and solve an integral expression for the area enclosed by the polar curve, 4 theta minus sine of theta, on this interval from 0 to pi. So again, a graph is not necessarily required to do this problem. It's helpful to know what this curve looks like. If this is a calculator problem, feel free to graph it on the calculator. You can also plot unit circles to kind of give a little picture for it if you think you need it. Again, you don't necessarily need it, but it is useful in some fashion. Okay? Just for the sake of time, I'll go ahead and show you what this kind of looks like. And we're going to be doing a lot of these things on the calculator anyway. You just have to set things up. On the AP exam, it would be like set it up, and then if you had to find the answer, most of the time it's on the calculator anyway. So this curve does something that looks like this, comes around and stops right there. And the first theta right here is 0, and the end theta right here is pi, from 0 to pi. And so it would be this region in here is the area. So we're taking little regions, sectors as we go around here, and then add them all up. So what is my area going to be? Well, my formula for the area is 1/2 the first angle to the second angle, r squared d theta. So r is this, my first angle is 0, my last angle is pi, and so my area is going to be 1/2 from 0 to pi, 4 theta minus the sine of theta, d theta. So this is the integral expression that you had to write, and then we can solve it using a calculator. And again, just when you do it on the calculator, make sure you use proper units and all that stuff when you do your integration symbols. Okay, text it out on the calculator, make sure you can do it, and you should get 70.902. So let me know if you do not, so we can go over that. Okay. Here's another one. Same thing. Most of these are just all going to be write the integral expression and then solve on the calculator. So here's this one. Write and solve an integral expression for the area enclosed by one petal of the polar rose. Okay. So let's take a look at this and see if we can figure out what that looks like. It's a polar rose. This number is even, so I know there are 4 of them. So then I know that this is going to be, basically goes like this, and it goes around right on these axes like so. So we'll have 4 of them, okay? And we need to figure out how to get one petal. So this one right here is one petal. And where does it start? It will start right here in the creation of this petal at theta equals 0. So when does it get here? When does it come here? How do I find these? That's the whole point of your areas. Then at this point is trying to figure out what is my limit of integration going to be. There's a couple of ways to do it. The whole polar curve is drawn from 0 to 2 pi. That's why this is important to know those from before. It will go all the way around this circle, just like I drew it, in this little spiral fashion, and end right here at theta equals 2 pi. So I can go from 0 to 2 pi. And when I do, I'm going to get the area of all 4 petals. Since I only want one petal, I would have to divide my answer then by 4. So my area is going to be 1/4. Okay, and then from 0 to 2 pi, 1/2 r squared, which is 3 times the cosine of 2 theta squared d theta. So that's how you can do this problem right here. So all the way around, and then take 1/4 of it to represent 1/4 of the petals. When you do, you should get a value that's about 3.534. But this is symmetric, both x-axis symmetry and y-axis symmetry. Okay, so how can I get these things, this petal, without having to go this way? Can I do it another way? Basically what it boils down to. And the answer is yes. From here to here, this angle in here that ends right at the pole, that is theta equals pi over 4. Because if I take pi over 4 and I plug it in here, the 2 and the 4 reduce, it gives me pi over 2, and that's a 0. Well, can I find another way to draw this piece? And the answer is yes also. Instead of ending at 2 pi, this piece can be drawn by looking at theta equal negative pi over 4. So normally we go in a in the counterclockwise direction, but negative angles go in a clockwise direction, remember? So I can go to negative pi over 4, it puts me right back in here also, and that just generates this one petal. Okay? And so then I can write it in that fashion as the area equals 1/2 from negative pi over 4 to pi over 4 of 3 cosine of 2 theta squared d theta. So that's another way to get the same answer. Either way it's fine. Okay, but pay attention to the angles and how these things are drawn. Okay, and another question right here. Same question basically repeated here. I'm just giving you different looks of different things. Write and solve an integral expression for the area enclosed by the smaller loop of this graph. So this is one of those limitations, and so then this, if you graphed it, okay, what's going on here is you have this curve is coming around like this, coming around like that, and then you have this inner loop. So I want that piece right there. Okay, so to find that, they cross right here at the pole. So we want to find out when is r equal to 0 in this equation. Well, r will be 0 when 1 plus 2 the sine of theta equals 0, or when the sine of theta equals a negative 1/2. And and one time around the circle from 0 to 2 pi, when does that occur? That occurs when theta is equal to 7 pi over 6 or 11 pi over 6. So that means it's going to start at 7 pi over 6 and it will end at 11 pi over 6. And that gives you two angles for your limits that you're going to need. So here's the 1/2, 7 pi over 6, 11 pi over 6, 1 plus 2 sine of theta squared d theta. And we can use a calculator again to work those out and get that answer right there. So we have to find that point where they close the loop. So the loop starts and ends when? That's the angle stuff that you need to focus on. Where does this region start? What angle does it start at? What angle does it end at? Okay? In this example right here, this is kind of in the realm of the next stretching that we're doing. So technically this is a region between two curves, the upper curve and the lower curve, theta equals 1. But since theta is an angle and it's the start angle, then we can get by with just doing this in the fashion that we're going to do it right here. Okay? So starts at angle 1, ends at angle pi over 2. And so that's how we deal with this problem right here. And so what is my area going to be? 1/2 from 1 to pi over 2 r quantity squared d theta. And so then I can type it in the calculator, because this would be very difficult to do otherwise, and get an approximation for that. Okay? So again, this is kind of technically the region between two curves. And so now we're going to officially go into that region, and I'll also show you the notes I had for this problem right here as we go through it. So there's the original problem, the notes I wrote, which is what I was saying. This is a region between two curves, but since one curve is the angle 1, the boundary is taken care of in the limit of integration. So let's take a look at this one. So now we're going to look at the area of a region bounded by two polar curves. So let's just go ahead and take a look at it. This is an example illustrating my point. Okay. Well, I'm showing you the example, so I was going to work it out, but here it is. So we want to, so the picture was given in that fashion right there. That's how it was illustrated right there. So the first thing you have to do is kind of identify which curve is which, and what angles do we start at and end at. Okay, so that's what we're doing right here. So identify which curve is which, just basically plug in a value into each of them to see which one you get. So here's angle pi. This outside curve is at 3, the inside curve is at 2. That gave me a place to look at. I don't want to choose pi over 2 because they both end and start at the same spot. I could have chose 3 pi over 2 to help me figure out which one was which. Either way is fine. Either way you look at it, you want to plug in a number. So this inside curve will give you a 2 value. The outside curve will give you a 3 value when pi is plugged in. And that tells me which one is which. Okay. The next we want to identify is the interval for theta. Where do these curves start? Where do they end? If I start at, all angles start at 0, and if I sweep around, the first angle I come to would be pi over 2. So pi over 2 is where it starts, and then as I sweep around the angles, the last angle I get to is 3 pi over 2. So that would be my interval. Okay. And likewise, from before in rectangulars, how do I get this region in between? Okay, well, think of a sector. It's the outside sector approximation minus the inside sector on that same angle sweep. Okay, so it's the outside curve minus the inside curve. Okay, and so then here we go. So the outside curve minus the area of the inside curve. That's the setup. That's the most important part. Then you plug it in the calculator and it gives you this answer over here. So that's the area between two curves problem. Okay? Identify your curves if you don't already know. Identify the angles that you're going to use for your limits, your upper and lower limits of integration. Make sure you set it up properly. Then you can use the calculator to approximate. So with that, let's do that one. The graph of the polar curves, r equals 3, so that's the circle. That's the circle of radius 3. And r is 4 minus 2 sine of theta are shown. The curves intersect at pi over 6. So at this point they intersect, and over here they intersect. That's the angle pi over 6. That is the angle 5 pi over 6. Let S be the shaded region that is inside the graphs of both the circle and the shape. That would be the part that I have shaded. Find that region. Okay, find that region. So you look at this, and there's a lot of ways to do it. Okay, but look at it closely and see what it is. How do I get that shape? Okay, forget trying to think integration. Just think about how do I get that shape that's there. It is the shaded region that is inside the circle, but also inside this cardioid shape. Okay? So how can I get it? Well, if I took the area of the entire circle and subtracted this top part, then I will have the part of the shaded. To me, that's the easiest way to do it. Okay? I'm not going for the shape directly. I'm going to take the entire circle, which is easy for me to find, pi r squared. Okay? And then I'm going to remove this top piece, because this top piece is, if I find the area of that thing, it starts at pi over 6 and ends at 5 pi over 6. Okay? And so that makes it a little bit easier for me to find these things. And that's what I end up doing. So my area is this circle minus the area of the region, not S, between pi over 6 and 5 pi over 6. And so then the area of S is the area of the circle minus 1/2 from pi over 6 to 5 pi over 6. Okay, and it's the area of the circle, or it's the 3 squared minus 4 minus 2 the sine of theta squared d theta. R of the circle, R of the shape, the cardioid. The outside minus the inside. That's not. That minus that. Because we're finding the area of this piece up here. It's not shaded. And so once I have that, and I type it all in, my calculator, don't forget this out here, 24.0709. So these take some practice to think things through a little bit, but that's pretty much how this works. I have one more example to do. This last one right here. The graph of the two polar curves, r2 times the cosine of 3 theta, and r equals 2. So I have that circle and this rose curve. What is the area of the shaded region? So quite clearly to me, it's the area of the circle minus the area of the rose curve, and it gives me everything left over. Okay, and so then that's what I'm going to use. So my area is the area of the circle, pi r squared, minus the area of the rose curve, which is 2 cosine of 3 theta squared d theta. Okay? So how do I get and generate this rose curve? What is my angle measurements that create the whole thing? This is where it's important to pay attention to what those curves do. Because this is odd, it generates the entire curve from 0 to pi. If I continue from 0 to 2 pi, this rose curve is generated twice, and I would have too much area here. So I have to go from 0 to pi. This one is already done, so you don't have to worry about that one. And so then you type that in the calculator and you get your answer there. Okay? So it's important to kind of know the characteristics of these certain pedals so that when you do your work on the AP exam, you'll be good to go. So let me just show you these notes so that you can pause and copy them down if you need to. This is just talking about the same thing I was telling you about the rose pedal. Odd, 0 to pi, even, 0 to 2 pi. Okay? And I'm going to back up a little bit for the last note, the previous example. I had some notes down here at the bottom that you might want to have too. Okay? And so that concludes the area problem that you'll be seeing, hopefully on the AP exam. And we'll take more questions in class.